Let us then tackle the general case in which we have a function f of x, and we want to generalize to fractional orders the notion of derivative. As you know, by definition, the first derivative of f is given by a limit, if that limit exists, of course. A limit as h goes to 0 of this ratio. As you also know, if we restrict h to positive values, we will be in the situation that I'm going to depict. Let the point at which I want to know the derivative be this x here. This is f of x. Since I am restricting h to positive values, x minus h will be to the left of x. This distance is h, and as h, which is larger than 0, is approaching 0, x minus h approaches x from the left. This quotient here, which is the slope of this line, will approach, as h goes to 0, the slope of the tangent at point x. This is what I call a left side derivative. On the other hand, if I restrict h to negative values, then x minus h will be to the right of point x. This distance here being h, which is less than 0. Here I will have my f of x minus h when h is negative, and since h, which is less than 0, is approaching 0, then x minus h will approach x from the right. This ratio here, which begins as the slope of this line here, will approach the slope of the tangent at point x, the tangent to the curve of f of x at this point at which I want to calculate the derivative. Of course, since the derivative is this limit as h goes to 0, without a restriction to positive or negative values of h, the derivative will only exist if this left-sided derivative and this right-sided derivative both exist and are equal. Or else, of course, if the function is not defined for one of the sides, in which case the derivative will be the derivative on the other side, the only side that does exist. This said, let us find an expression for the second-order derivative, which is, as you know, the derivative of the first-order derivative of function x. So we can apply this expression and write the following. We will now apply it 2 times more to write as follows. Since I already have here the limit, I do not have to repeat it. I only have to keep the limit once. H multiplied by h gives me h squared. And as to the numerator, I will have f of x. I will have minus f of x minus h twice. And then I will have plus f of x minus 2h. This said, we will now find an expression for the third order derivative. We will proceed in the same manner. The third order derivative is, by definition, the derivative of the second order derivative. So I can apply this expression, and then I can replace this expression I have just found twice. Let us then simplify this just as we did for the second order derivative. We only need the limit once. The denominator will be h power 3, and the numerator stays as follows. We might proceed to the fourth order derivative and to the fifth, but these cases we have here suffice, especially if we add to the third, second, and first order derivative the derivative of order 0, which is, of course, the function itself. I divide the function itself by h to the power of 0, which is always 1 if I write as well a limit here with h going to 0. If h goes to 0, then h is different from 0, and consequently, whatever real value h may take, this is always 1. Let us then take a good look at these expressions we have found. We have the derivative of order 0, and we have this, the derivative of order 1, for which we have by definition this. For the derivative of order 2, I have this expression here, and for the derivative of order 3, I will have this expression here. Well, what I see is that I always have a limit as h goes to 0. That in the denominator I have here h power 0, h power 1, h power 2, h power 3. It is always the order of the derivative itself. In the numerator, I have here 1, 2, 3, 4 terms. So the number of terms in the numerator is always the order of the derivative plus 1. Let us write this here as the general case of the derivative of order n, as the limit as h goes to 0 of h power n, and here a summation that will have n plus 1 terms. How am I to count those terms? Here I have f of x, and I always begin with f of x. Then I have f of x minus h. Here I go up to x minus 2h, here up to x minus 3h. That is to say, I subtract up to x minus a multiple of h given by the order of the derivative itself. Consequently, here I will put k, a dumb variable, that begins at 0 and ends at n, the order of the derivative. Here I have my n plus 1 terms, and I will have here f of x minus kh. I begin with f of x and subtract multiples of h up to nh. What about those coefficients here? I will write them in this corner, and you will surely recognize them. For order 0, I have 1. For order 1, I have 1 and minus 1. For order 2, 1 minus 2 and 1. For order 3, I have 1 minus 3, 3 minus 1. And we could, of course, go 1, but this should suffice to show the following. First, the signs alternate on each line, always beginning with a positive value. Consequently, I can write here minus 1 power k. In this way, for k equal to 0, I will have a positive sign, and from then on, I will alternate a plus with a minus until the end. As to the absolute values of these coefficients, you recognize them because they are the numbers in Pascal's triangle. Consequently, what I have here is, in fact, the combinations of n,
k at a time,
n, the order of the derivative, and k, the dumb variable in this sum. This expression gives me, in fact, the derivatives of order 0, 1, 2, 3, and so on. You can find the derivative of order 4 and check that it follows this. The same for order 5. The proof, of course, is by mathematical induction. We apply a first-order derivative to this general expression we have just found, and we show that the result will be the very expression itself for n plus 1. This expression seems to make sense also when n is not a non-negative integer. We are thus tempted to write that f derivative of order alpha is given by this. Indeed, h power alpha makes sense even if alpha is not integer. These combinations, we have defined them using the gamma function. The only question that is left is, how far should I take this summation? We have here something that we do not know, because in this case we have the order of the derivative itself, which is an integer number. What about here? Should we round alpha to the nearest integer, but round it down, round it up?